Hello everyone, this is Mr. Hall and this is a really quick video about AR, MR and percentage mass. This is one of the foundation bits of knowledge that you need to know if you're going to tackle anything with regards to quantitative chemistry. So from here on in, you need to know this stuff to learn about moles, reacting masses, limiting reagents, you name it. So hopefully it's relatively straightforward, this stuff, but it's really fundamental stuff you have to know. So by the end of today's lesson, you should be able to know the three things. You should be able to deduce the AR for an element using the periodic table. You should be able to deduce the MR of any substance, element or compound using the formula and also AR data. It's pretty straightforward, those first two. And then finally determine the percentage mass of a given element in a compound, which is also relatively straightforward, but you just need to know how to do it. So before we go any further, let's think about the molecule water. Now water has the formula H2O, which you may know, and it should look a little bit like this if you were to draw it out based on the formula. Now the formula tells us that this molecule contains one atom of oxygen and two of hydrogen, and as you can probably work out, this is one hydrogen, this is the other hydrogen atom, and this is the oxygen over here. Now the diagram, however, is quite inaccurate, and it's basically because of the size of the atoms. Now we know there's more hydrogen atoms than oxygen atoms, but oxygen's a lot bigger, partly because of its larger number of electron shells and because it's got a much larger nucleus. So as a result, if I was to redraw it more accurately, it would look a little bit like this, where your hydrogens would be very small and your oxygen would be much larger. Now, we're not going to spend too much time today looking at the electron structures because that's for another video. But what we'll look at much more is to do with the actual mass of the atom themselves and how they differ with different elements. So let's start off with AR. Now, AR is just another way of saying how heavy different elements are compared with the mass of one atom of carbon, which we give the number 12. So 12 grams of carbon is basically the same as 1 mole, which you'll learn about a lot later on. So if you look at the periodic table for any element, you'll see two numbers, as you know. The bottom number, or the smaller number, depending on how your periodic table is arranged, that's the atomic number, and that tells you the number of protons present. The larger number is your mass number, and that tells you the number of protons and neutrons found in the nucleus of an atom. Now, if I was to draw the full atomic structure of this element, it would look a little bit like this, where I would have 6 electrons, 1, 2, 3, 4, 5, 6, which matches the atomic number. I'd have 6 protons in the middle, so 1, 2, 3, 4, 5, and 6. And then I'd also have 6 neutrons, because you do 12 take away 6, which equals 6 neutrons. And your 6 neutrons will be here, so 1, 2, 3, 4, 5, and 6. Now the mass is all in the nucleus, okay? These electrons are basically considered to have no mass, essentially a negligible mass. So we can discount those when we're considering the mass of an atom. The mass of the atom is essentially concentrated in that nucleus. So just to summarize, if you want to work out the AR for any element, you just have to look at the periodic table and look at the mass number. Now MR is relative formula mass. And that's basically, for any compound or any element, it's basically just adding up the different masses together for each atom inside that substance using the masses from the periodic table. So, for example, if I've got the MR for carbon monoxide, if I look at the formula, I notice first off there are 2 elements and there's 1 of each. I've got 1 carbon and I've got 1 oxygen. So the first thing I need to do is to look at the periodic table in order to see what the masses are. So if I look at the periodic table, I see that there is carbon and there's oxygen, as you can see. Carbon's got a mass of 12 and oxygen's got a mass of 16, or AR if you like. So to work out the MR for this particular molecule, I would do 12 plus 16, which gives me 28, and that is your MR. Done. Okay, so that's a relatively straightforward example. Let's try another one. Here we've got to find the MR of sodium oxide, slightly more complicated. So we've got 2 elements again, we've got sodium and we've got oxygen. However, now we've got this number 2 here. Now this 2 tells me I've got 2 sodium, so I've got 2 of these, but because there's no subscript number next to the oxygen, that means I've only got 1 of those, okay? So to work out the MR in this case, first off I look at the periodic table as I normally do, and I find sodium and oxygen like so. Sodium's got an AR of 23, oxygen has an AR of 16, so now I'm in a position where I can work out the MR. So the MR for sodium oxide, I like writing MR and then the formula like so, I think it's tidy. So that would equal 2 times 23, add my mass for oxygen, which is 16. So that would equal 46, that's 2 lots of 23, plus your 16, which should give you 62. and that is your MR for sodium oxide, okay? So as you can see, it's relatively straightforward. There's one type of example which may throw you, and it's where you have things inside brackets, okay, such as this. So here we've got the question of finding the MR for magnesium nitrate. Now let's just break this down. The formula is MgNO32. Now what that basically means is I've got 2 lots of this NO3 polyatomic ion, or this thing. So if I was to write it out, draw it out rather, here's my magnesium atom, and it's got 1 NO3 over here, and it's got 1 NO3 over here. Okay, now if you count it up, you've got 2 nitrogens, so nitrogen is times 2. I've got 3 oxygens over here, 3 oxygens over here, so my oxygens is times 6. Now you can actually work that out if you look at the formula, because you can see there's no number between the N and the O, so we basically consider that to be 1 nitrogen. I've got 2 lots of that, so 2 times 1 equals 2, and that's for nitrogen. With oxygen, I've got 3 of them in the bracket, but I have to multiply that by 2, so 3 times 2 gives me 6 oxygen atoms. So you can work it out either by drawing it out if you want to be really sure, or you can do the mathematics like I've just shown. Anyway, the first thing I need to do is, now I've established that, I need to now find the elements on the periodic table to work out the ARs. I do that and I find them as being so. So magnesium's got an AR of 24, oxygen 16, and nitrogen 14. So now I can go ahead and start doing my calculation. So my MR for MgNO32 is, start with the magnesium, which is 24. There's only 1 of them, so we don't have to do anything too fancy. Add, now oxygen has got a AR of 16. I've got 6 of them, so 16 times 6. There we go. And then I add the nitrogen, which I have 2 of, so it's 2 times 14. Okay, so I put that, I simplify it a bit more, so 24 plus 96, I think. And then add 28, and then the sum of those numbers, let me just get my calculator because I'm to work this out, is, let's put this in, so 24 plus 96 plus 28 equals 148, okay? And that's my MR. Okay, so you can see that that's pretty much as bad as you're going to get, all right? But the one thing I would recommend is just show your working. Showing your working goes a long way, particularly if you make a mistake later on in the question, you'll still get credit for the fact you tried to break this down. Okay, now, if you look at the following equation, we've got hydrogen combusting to form water because it's reacting with oxygen. If I spend some time working out the MR of the reactants and the products, hydrogen has a mass of 1, all right, and oxygen has a mass of 16. So to work out the MR, it would be 2 times 1 times 2, because I'm also including the coefficient, plus 16 times 2. So I don't know why that thing's there. And that would make 2 lots of hydrogen, like 2 lots of 1 is 2, let's kind of make a shortcut there, plus 16, all right? Now, if I was to simplify that down here, that would be 2 times 2 add 32, all right? And that would be the same as 2 lots of 18. Therefore, that would be, let me make sure I get this right, actually. Yep, there we go. Get rid of that. That makes sense. So 2 times 2, which is 4, plus 32, and that's the same as 36, and then 32 plus 4 is 36. Okay, so 36 is the same as 36. So what I'm trying to show you here is that the MR of your reactants is the same as the MR of your products. And that makes sense because that's consistent with the conservation of mass, which basically says that whatever you start with, you end up with. You cannot lose or gain matter in any chemical reaction. Okay, so just to clarify, the MR of the reactants and the products is always the same, the total anyway, and that's consistent with the conservation of mass. That's something which you may be asked, and it's always worth bearing in mind. The final thing I want to talk about today is percentage mass calculations. Now, to find percentage mass of an element in a given compound, you need to divide the total mass of that element by the MR of the compound. And I've got an equation here which is worth noting down. It's relatively straightforward. You have to multiply it by 100 to get a percentage. So let's do an example just to show how this works. So this says find the percentage mass of carbon in carbon dioxide. So the first thing I want to do is work out the MR. So using the periodic table, I find the 2 elements. So the MR of CO2 is going to be 12 plus 16 times 2, which I think equals 44. All right? So, yeah, it does. Now, to work out the percentage mass, I first off have to work out how much carbon is in carbon dioxide. Now, there's only one atom of carbon, which is a mass of 12. So the total mass of carbon in carbon dioxide is 12. I then divide that by the MR, which in this case is 44. So I do 12 divided by 44, and then I times that whole thing by 100. So if I whack that into the calculator, so 12 divided by 44 times 100, and I'll round it to 3 significant figures, so it's 27.3, I think. Yeah, 27.3. So what that tells me is that 27.3% of the mass of that compound is carbon. The rest of the mass, the sort of 70 odd, is oxygen, which means most of the mass of carbon dioxide is oxygen, which makes sense. Okay, let's try a couple more problems. Find the percentage mass of sodium in sodium oxide. Okay, similar problem. So again, I go get my ARs first of all. Sodium is 23, oxygen 16. Now, if you look at this, we first off have to work out the MR. So the MR is 23 times 2 plus 16. So that, I think, gives you 62, if I'm not mistaken. Yeah, 62. Now, I now have to work out the percentage mass of sodium. It's always good underlining and annotating your question when you're doing this, just to make sure that you're making sense. Now, I need sodium. Now, sodium, there are two of them, as you notice from the formula. So the mass of sodium is going to be, I'm just going to write Na here. Let's write AR of Na. That'll equal 23 times 2, which equals 46. So when I do my percentage mass calculation now, because I want to work out the total mass of sodium, I have to use the 46, not just 23. That's a common mistake that's made. So it's 46 divided by the MR, which is 62. I times that by 100, and that gives me to 3 significant figures. Let's find this out. 46 over 62 times that by 100, and that gives me 74.2%. There you go. So I hope that's been useful, and best of luck with your AR, MR, and percentage mass calculations.